Hello, my name is Anthony Ricco. This presentation is being given for completion of the Advanced Topics of Computer Science Data Mining 1 course given at Rowan University, autumn 2016. Instructor is Dr. Anthony Brightsman, and the title of this presentation is Exoplanets and Their Host Stars, Data Mining and Discovery. Today I'm going to be talking about the project requirements, which are the statement of the problem, explain why people would care about it, explain primary objectives and the approach, discuss anything original about this research, and discuss conclusions and lessons learned. The statement of the problem. I wanted to aid in the physical and virtual hunt for new, potentially habitable exoplanets by comparing and categorizing known exoplanet features and features of their hosts. I also wanted to attempt to predict information that may be incomplete in the current exoplanet database. For instance, a space-based telescope finished its first observing mission back in 2013. 3 years later, scientists are still mining that data to confirm additional exoplanet candidates. So why would people care about this research? Why are host star characteristics important? Well, there are hundreds of billions of stars in the Milky Way galaxy, and there are many sources for that information, and petabytes of existing data. Categorizing and/or predicting as many stellar attributes as possible in the existing data may provide a roadmap for the particular stars or data on which to focus first. So if we find Earth-like planets, and if those planets are potentially habitable, then stars with the same properties may be promising candidates for additional habitable planets. The primary objectives and the approach were initially exoplanet-centric. I wanted to investigate locations and distribution of the confirmed near-Earth exoplanet hosts. I wanted to determine common, prevalent characteristics of those hosts. I wanted to learn how the exoplanets were discovered. And I'm going to answer that one first. There are multiple ways, but the most effective is called transit photometry. And that is the measurement of the minute dimming of a star's light as an orbiting planet passes between it and the Earth. Now, distribution of the planets and of the exoplanets and finding them on the celestial sphere. The celestial sphere was conceived of hundreds of years ago to describe the position of objects in the sky, when people still believed the Earth was the center of the universe, and the sphere rotated around it. Although we know differently today, it is still used because it's an accurate representation for locating stars, and it's just a fictitious sphere with an Earth at the center onto which all celestial bodies can be projected. Now you take the Earth's equator and you project it on the celestial sphere, and it becomes the celestial equator. Likewise, Earth's coordinate system of latitude and longitude become celestial coordinates of right ascension and declination. Right ascension is east and west, declination is north and south. All right, I have an example of plotting some stars. Initially, when I was doing research, I came across a constellation that was plotted on the Cartesian coordinate system. And I thought that would be a good introduction for me to get familiar with astronomical data, astronomical terms, and to begin plotting in that way before trying to tackle the larger database. So I obtained the coordinates of each of the main stars in the popular winter constellation of Orion. I converted each one of those coordinates to the units needed, and the results are there on the right. Now I'm glad that I began with this simple example because it took some trial and error to finally get the plotted constellation to resemble reality. Notice the x-axis, it doesn't go from 0 to 90, it goes from 90 to 0. And when I had it going the default direction, 0 to 90, well, that put the constellation backwards. So armed with this knowledge, the next step was finding the distribution of the exoplanets and plotting each one of them from all of the entire database. And this was very successful, but it illustrated something quite unexpected. And that is, why was there such a concentration in that area? So I needed to validate for certain that the data was being interpreted and plotted correctly. And to remove any errors introduced by my personal code, I looked only at the histograms of each star's location by rotation ascension and declination, and the results seemed to prove the previous observation was correct, because you can see the stars seem to be piled up in one location. So those data points could only mean that I needed to turn my investigation to the origin of the data itself. So I began to research how stars are searched for, how exoplanets are searched for, how the host stars are found, what instruments are used. And I came across the Kepler Space Telescope. It was launched in 2009, and it settled into an Earth-trailing orbit and fixed its gaze on a small patch of sky. And it stared at that small patch for 4 years. Now within that patch were approximately 150,000 stars, and Kepler was waiting to catch the tiny dips in the amount of light coming from the individual stars themselves, caused by the planets crossing in front of them. In other words, the transits about which I spoke earlier. The result was that more than 2,000 confirmed exoplanets were sifted from the data, the bulk of the 3,431 confirmed as of December 1st, 2016. And today, 4 years later, they're still revealing new planets in that data. Now, Kepler was pointed at the patch of sky near the Lyra Cygnus constellations, and the yellow portion on the right represents Kepler's field of view. Now, you may have noticed from the celestial sphere that Lyra and Cygnus are located in relation to Earth over on the left-hand side at that particular time of year on the celestial sphere. Doing a little bit more digging, I came across the Kepler focal plane, and this is just a plane of very sensitive optical instruments that are inside the Kepler telescope. And notice the geometric concentration and the formation that they have there, and notice how it matches up in the upper right. Then taking the next step, I took a zoom in on the data that I had plotted previously, and such a surprising result came out. I was quite amazed that I guess I was right, and I was plotting them correctly, and I was just very surprised by that very cool result. The only problem was that mining the exoplanet database to hunt for new individual stars was not only naive, but most of the observing techniques looking for the stars and the exoplanets are doing so at hundreds of thousands of stars at a time. Therefore, the goals of the project need to be reevaluated to discuss some other meaningful outcome. So I turned my inspection to the data, and I looked more closely, and it showed that every row in the database had an exoplanet entry with planet-associated information, but the host star information was missing. There were spotty and inconsistent information. Enter host star classification. So the project focus shifted to looking at the characteristics of the host stars using data mining classification and prediction techniques for the attributes such as spectra, temperature, metallicity, etc. So why are host star characteristics important? Well, as mentioned, there are hundreds of billions of stars in the Milky Way galaxy, and it would be very helpful to have a roadmap to determine the particular stars on which to focus first, as was already mentioned. Now, as a planet makes its transit across the face of a star, a sliver of starlight shines through the planet's atmosphere. And gases and chemicals in the atmosphere absorb different wavelengths of light as it passes through. So by looking for these missing slices of the star's light spectrum, scientists can tell which constituents are present in the alien atmosphere. So that will help to identify if a planet has an atmosphere that is capable of supporting life. So knowing host star attributes that have those types of planets orbiting them, those are candidates we'd like to look at. Now the approach and the details of the data mining tasks. The next tasks were to investigate the host star data, to import and pre-process it, to train various prediction methods, and to analyze the results and evaluate the methods chosen. Now, digging into the data, there was quite a bit of investigation done on the host stars, including plotting various characteristics in varied ways. And this eventually led to the plot as shown here. Now, I recognize this plot. It looked somewhat familiar, and I realized that it had a strong resemblance to the Hertzsprung-Russell diagram, which is also known as the Rosetta Stone of stellar astronomy. This particular diagram simply plots stars by temperature versus luminosity, and that band there from upper left to lower right is called the main sequence. All the stars in the galaxy have been plotted, all of the visible stars in the galaxy have been plotted with this and plotted in this manner, and they all wind up in this area, many of them on the main sequence. Predominantly they're on the main sequence. Now as they enter different stages in stellar evolution, they will migrate. For instance, the sun, as you see there toward the center, as it ages and begins exhausting its fuel, it will move up to the right and up and become a giant. It'll then, after that, it'll become closer to the supergiants, although it will never become a supergiant. And then eventually, once it exhausts all of its fuel and it can no longer have the thermonuclear reactions in its nucleus, it will drop down to the cool, dim region in the lower right-hand side and become a red dwarf. Now, plotting temperature versus luminosity for the host stars in the exoplanet database turned out to be a zoomed-in look at the Hertzsprung-Russell diagram. And you can see there the scales are slightly different, but the sun there at luminosity equals 1 would be there on the right. And that was another kind of a cool find, and it was kind of telling me that I was on the right track, and it was another warm fuzzy for this research. Now, the details of the data mining. I need to import and pre-process the data. And although the data started out with more than 3,400 rows, many of the rows were missing information. In the case of some rows, only one column was missing information within the row. So after consideration, calculating a mean or otherwise guessing at some surrogate value for that missing information, it just was not chosen as a viable solution. So that unfortunately meant if a row had even one missing entry, the entire row was deleted from the database to be processed. Now, there are pros and cons with that approach, of course. Small data sets are obviously a drawback in modeling. However, the advantage is that as more complete data is introduced, and it no doubtedly will be, the models and code will remain unchanged. Now, using the scrub data, neural networks were trained and tested using the R neural net library. Additionally, in order to evaluate the effectiveness of the neural network, a generalized linear regression model was also created using R's GLM library. The predictions were then compared and evaluated. For example, the neural network technique for the star spectral class yielded an error rate of approximately 0.045. Model evaluation using generalized linear regression was then performed. Unfortunately, the spectral class input data is continuous, but the library for linear regression requires min-max normalized data. Therefore, for direct comparison, an additional neural network working on min-max normalized data had to be created so that the neural network implementation and the generalized linear regression model implementation could be directly compared. And then they, in tandem, could be compared with the continuous data neural network. Now, once a prediction is obtained using min-max normalized input, it is continuous and must also be min-max normalized for comparison against the normalized input. So min-max normalized data is input into a generalized linear regression model. The data out of that model is continuous, and it must be min-max normalized again. However, it's unclear what value to use as the cutoff for setting the prediction result to 0 or 1. For example, take a look at the following code snippet in R for min-max normalization of a prediction. This is an inline function, and you can see it takes as its input the linear regression guess, that's the continuous data, and the variable b accepts that value, those values. It's actually a vector. So for b, as each one of the vectors is incremented through, it's compared against a particular value, and it's a 0 is returned if the value is less than, if b is less than that value, or if 1 is returned if b is greater than or equal to that value. The question is, what should be used as the cutoff? What should be used for that comparison? So to aid in finding the best value to use as the cutoff, min-max accuracy, to aid in finding the best value to use as a cutoff for maximum accuracy or minimum error, a confusion matrix was used. However, instead of trying to guess at the best cutoff to maximize accuracy, an R function was written which accepted, among other things, a range of cutoff values, including min and max. Now, that function then computed the confusion matrix for every cutoff, saved the cutoffs that achieved the highest accuracy, and plotted results. So you can see there for, on the left-hand side, the stellar spectra, the neural net for the continuous data. You can see that the maximum accuracy occurred at, the first time it occurred was at 0.66. So that would be the value used there for the comparison. What should be used here in this particular case for the neural network? 0.66. So using the best cutoff obtained, the lowest error rate in turn was calculated. And as we know from our examples, all you do is you take the false positives plus the false negatives over the entire sample. And that gives you, for the stellar spectral class, an error rate of 0.07 approximately. Now here are two excellent examples demonstrating the value of the function to find optimum cutoff for maximum accuracy, or in other words, minimum error. And this implementation proved extremely useful in this investigation because you can see there on the left that it would be very difficult to guess at the maximum accuracy for the optical magnitude. You can see it's way over there on the far right, almost at 1. It would have been very difficult to guess that. Now the predicted attributes of the host stars and error analysis, best to worst performers. This table represents from left to right the host star predicted characteristic, and that they are temperature, spectra, and metallicity. Those are the top 3 performers. And then there were a few issues I'm going to get into with luminosity, mass, radius, and magnitude also. Next column over is the neural network continuously normalized error rate. So the error rate for the neural network continuously normalized data. Next over is the error rate for the neural network min-max normalized data. And finally, the linear regression error rate. Again, min-max normalized data. So you can see that the top 3 performers there, temperature, spectra, and metallicity, they're quite good. And there's a good bit of confidence. The error rate 0.025 is quite good. Spectra and metallicity, they begin to get a little higher, but they're fairly good. And what's even better is that those models match. And that's instilling confidence that these predictions are actually on the mark. Now with luminosity, mass, radius, and especially magnitude, well, I began to have problems, and these results are not perfect. I received a warning message from the GLM function, fitted probabilities numerically 0 or 1. What that meant was that the predictions, where they're supposed to be continuous, it turned out that they actually only predicted 0s and 1s. So that those data points were just not valid. Then a very detailed inspection was performed on radius, and that showed that the input seemed reasonable, but there were several predictions with error rates over 100%. Now many predictions were low, but the outliers brought the overall prediction into question. Now, the analysis of optical magnitude showed it had by far the highest number of unique values among the variables above. And while the neural net and linear regression prediction libraries are black boxes to the caller, it is reasonable to conclude that the libraries had difficulty calculating accurate predictions due to the number of unique values, because there are fewer discernible patterns. And it is a guess, but these fewer discernible patterns led to higher error rates and low confidence in the predictions. So lots of different unique values, more difficult to predict what the outcome would be. Now, the conclusion of the analysis is that although the poor performers above will not be used to predict information in the existing exoplanet database, the fact that all three implementations are in agreement for temperature, spectra, metallicity, and even magnitude instills confidence that the implementations and models are reasonable. Now, the summary and takeaways. Multiple prediction models are in agreement. Error rates for temperature, spectra, and metallicity are low. Confidence is good that their predictions. Confidence in their predictions is good. Recommendation is models of the neural network trained with continuous normalized inputs are sufficient for predictions of these stellar attributes in the current exoplanet database. Now, models using min-max normalized inputs should be used as a validation of continuous model only. And min-max normalized models should not be used as a primary models because the input data for all of these attributes are continuous and not binary in nature. What is original about this research? Well, after learning that more was recorded in the database about the planets than the host stars themselves, as mentioned, the focus changed to predicting that missing information. And this apparently is not being done, or at least it's not advertised by the astronomical community, giving rise to the opportunity for potential new research. Overall conclusions and lessons learned from the data mining perspective. Selecting the best cutoff for normalization was critical, and with this data in particular, even more so than tuning the neural network. In that picture there on the bottom of the screen shows the most complicated neural network that I achieved while tuning the neural networks. But it turns out that that really didn't provide any better value, didn't provide any more accurate neural networks than far less complicated ones. It turned out that time was much better served trying to find a better cutoff for normalization. The next point, a very memorable lesson learned, was calculating error using negative and positive data, especially when that data can be zero. So you have your input, it can cross zero, it can be negative, it can be zero, and it can be positive, and they're all valid inputs. Well, I needed to recall that the error rate is calculated as predicted minus actual over actual. When actual can be zero, your error rates can go to infinity. And it took a little bit of investigation on my part to finally determine where my problem was, and it was in my error calculations, not in my modeling. Biggest conclusions learned from an astronomical perspective? Well, the biggest one was exoplanets are not searched for on an individual basis, and that was, I guess, a rather naive thought now that I know it. Instead, hundreds of thousands of stars are monitored in a single field of view, and the data is poured over for years. And probably the biggest takeaway from this, from my perspective, was seeing the successes of plotting both the host stars and the exoplanets with respect to the Earth. And I just thought that was a really cool find, and I learned quite a lot in choosing this topic. Okay, thank you for listening. And petabytes of existing data. Categorizing and/or predicting as many stellar attributes as possible in the existing data may provide a roadmap for the particular stars or data on which to focus first. So if we find Earth-like planets, and if those planets are potentially habitable, then stars with the same properties may be promising candidates for additional habitable planets. The primary objectives and the approach were initially exoplanet-centric. I wanted to investigate locations and distribution of the confirmed near-Earth exoplanet hosts. I wanted to determine common prevalent characteristics of those hosts. I wanted to learn how the exoplanets were discovered. Hello, my name is Anthony Ricco. This presentation is being given for completion of the Advanced Topics of Computer Science Data Mining 1 course given at Rowan University, autumn 2016. Instructor is Dr. Anthony Breitzman, and the title of this presentation is Exoplanets and Their Host Stars, Data Mining and Discovery. Today I'm going to be talking about the project requirements, which are the statement of the problem, explain why people would care about it, explain primary objectives and the approach, discuss anything original about this research, and discuss conclusions and lessons learned. The statement of the problem. I wanted to aid in the physical and virtual hunt for new, potentially habitable exoplanets by comparing and categorizing known exoplanet features and features of their hosts. I also wanted to attempt to predict information that may be incomplete in the current exoplanet database. For instance, a space-based telescope finished its first observing mission back in 2013. 3 years later, scientists are still mining that data to confirm additional exoplanet candidates. So why would people care about this research? Why are host star characteristics important? Well, there are hundreds of billions of stars in the Milky Way galaxy, and there are many sources for that information. And I'm going to answer that one first. There are multiple ways, but the most effective is called transit photometry, and that is the measurement of the minute dimming of a star's light as an orbiting planet passes between it and the Earth. Now, distribution of the planets and of the exoplanets and finding them on the celestial sphere. The celestial sphere was conceived of hundreds of years ago to describe the position of objects in the sky, when people still believed the Earth was the center of the universe, and the sphere rotated around it. Although we know differently today, it is still used because it's an accurate representation for locating stars, and it's just a fictitious sphere with an Earth at the center onto which all celestial bodies can be projected. Now you take the Earth's equator and you project it on the celestial sphere, and it becomes the celestial equator. Likewise, Earth's coordinate system of latitude and longitude become celestial coordinates of right ascension and declination. Right ascension is east and west, declination is north and south. All right, I have an example of plotting some stars. Initially, when I was doing research, I came across a constellation that was plotted on the Cartesian coordinate system.